Hi, today we're going to talk about functional safety and specifically the FMEDA analysis inside functional safety. Now, to give context on what this is, functional safety has these main analyses in it, which are the FMEDA, FMEA, and the other requirement spaces. And these are different from each other, the FMEDA with the diagnostics and with the FMEA. The FMEDA has data and it uses this quantitatively rather than the qualitative FMEA that you would use with expert knowledge and brainstorming with stakeholders. The FMEDA can be done with different tools. Today I have made my own tool for it because, frankly, there was no good information on the internet about how to make this. So I decided to make my own YouTube video. And other tools that you could find would be, for example, from ExceDA, or you could possibly use Markov modeling, which is also possible in the standards. Functional safety is based on the triage of FMEA, FMEDA, and other requirements bases. Based on my experience, the FMEDA takes about 5% of the time, FMEA another 5% of the time, and the other requirements take 90% of the time. The FMEDA and FMEA are rather small compared to all of the other requirements, managing them and doing the validation on those items. But they are the qualitative and the quantitative measures that guide your safety decisions, which is why it is very important that this analysis is understood, because this is what guides your safety. This is what actually makes concrete safety decisions for you that you cannot go without. Functional safety is normally split into the industrial category, the process safety category, and the automotive industry. These standards are the 61508, 61511, and the 26262, of which the 26262 is the most known. My knowledge is specifically on the 61508 or the industrial section. These standards differ from each other in that in the industrial context we look at only one failure occurring at a time. In the automotive context, however, there can be two failures. That is why the automotive context is a lot harder to make functional safety devices for, because the standard itself is a little bit more strict. So, let's start off by going straight into the Excel.
The FMEDA shows each component, and all of the failure modes of that one component are described here. For example, we will go through one resistor here. There is the resistor R1 picked from our schematic, which has failure modes given to it from our data source. These failure modes are short circuit, open circuit, half, and double the resistance, and these are the associated failure in time measures. Next, we go to classify them based on our circuit into safe, dangerous, and no effect failures. The second column then takes this diagnostics into account, and they will use this diagnostic coverage to multiply with the amount that we have in here. The one here selects into the safe and multiplies by the diagnostic measure to get the safe undetected and detected. And the dangerous failures here multiply with the diagnostic measure to gain the dangerous undetected and dangerous detected. The formula is as follows. I sum whether it is dangerous, yes, no, or safe, the quantities, and then multiply it by the diagnostic coverage. In the end, we will go through all of the components and all of the quantities, and we will arrive at these columns that are summed together. We will especially want to calculate the subsystem undetected failures. This column, sum them all together, the dangerous detected failures, and as the standards do not require us to decipher are the safe failures actually detected or undetected, we can just select all of the safe failures. And from those left columns, we can calculate the safe failure fraction for this subsystem. This subsystem safe failure fraction is limited by our architecture, and you should verify it against your own architecture. We will go through each of the subsystems one by one. For example, here in output processing, I have added a relay that we have data from the manufacturer directly, and we have a manufacturer given high diagnostic coverage for the associated somewhat high failure rates. And these will result in their own subsystem safe failure fractions and the undetected failures. Once all of the subsystems have their own data put into these fields, you can bring that to the top level where we have the secretive PFH calculation. The PFH is given in the standards as a calculation for the simplistic mode. We can also calculate it using, for example, Markov modeling. And all this is intellectual property of the standards, and for legal reasons, I cannot show you the formulas. Instead, you can go view these formulas by purchasing the standard 615086 and viewing the subsections shown on screen. With that PFH, we can calculate the total system PFH by summing together over the architecture that we have. For example, I have chosen to have no redundancy for my input processing and logic, which means they are a 1 out of 1 system. For my output processing, however, I have chosen to have 1 out of 2 redundancies. We can then sum these numbers up to gain the system PFH. And the total system SFF can be gained by going and actually viewing the data that we have, which is the fetch data from those bottom requirements, and summing over each of those. That will give you the total system SFF. And these two values are going to be the values you list in your safety manual. Now, you might be wondering, what are all of these numbers here? The formulas, in order to work, you have to give them parameters. And now the parameters are the proof test interval, which you can play with. You can give it shorter times, you can give it longer times. That shows you how they are affected, for example. Then you need to give them the mean repair time, time to restore. And for each subsystem, we are going to have a beta factor which relates the dangerous undetected failures to common cause failures. And then there's also the detected ones, but this has little to no effect. Now let's next talk about the data that is involved. One way to get data is from the military handbook of MIL HDBK 217F. The military standard gives you a multiplicative factor by taking to account the base failure rate, different factors for quality and environment, but this gives you rather pessimistic approach. I use here as an example a resistor for fixed resistor general purpose low power, which I have taken data for from the Exida CRD for resistor 1, and for the military standard I have applied the ground-based non-military standard general purpose resistor. Now, the problem in this military standard is that it does not have real failure modes, it only gives you the failure rates. So we will have to assume a 50-50 split for the case of the military standard, which also is not very helpful for diagnosis, because we will have to assume that these failures will occur. And now the pessimistic thing I was talking about can be viewed from the failures that this military standard produces. We can see that the failure rates estimated are more than 5 to 10 times higher than for the data gathered from EXIDA. Keep this in mind while doing your analysis, because garbage in leads to garbage out. But, of course, too pessimistic leads to you being very pessimistic with your approach and designing in very much margin. In the end, I would also like to mention the effect of the diagnostic coverage on our calculations. Any diagnostic coverage that you claim to be more or equal to 90 will have to have associated failure injection testing or fault injection testing. It is also not best practice to call all diagnostics high diagnostic coverage. In fact, there is a standard clause that will limit your claimed diagnostic coverage, and you should follow these limits when given any diagnostic measure a DC value.
Thank you for your interest in the matter of functional safety. Now, this was my very first YouTube video ever, so pardon me if there are some troubles in the video or the comprehension of it. Ask anything in the chat if you want to see more. Next, I think I will make a video about how to actually use this data in decision making, how the numbers actually go on with each other and what makes the decisions happen.